topics for the quiz. Not the whole class, with a few minutes. The quiz, as before, is going to be a short little, 15-minute thing. Take a few minutes break to get the adrenaline out of your system, and then we resume at 11:30 for anyone who doesn't have to take a quiz and wants to come a little later. Okay, so we've basically since the midterm done book one, right? Not even, basically book one. Okay, so I think, no, we went a little further. Okay, let's see. We talked about book one. What do we talk about book one? The structure of the book one. It has these definitions that don't really define since they can't. It has the postulates, the famous postulates. The first four being very simple, and then there's the famous fifth postulate. So fifth postulate, know the statement, right? No, bless you. No, bless you. The statement. What's the statement of the fifth postulate? Two lines. Right? How do we measure their non-parallelness? Right. The sum of the interior angles, exactly right. So the statement, I'll just draw it, but you guys should be able to communicate it. If the sum of interior angles, so if alpha plus beta, if this is alpha and that's beta, add up to less than two right angles, then what?
Then the lines on the side where the angles are only.
Exactly. Then they intersect. Okay, so he's very worried about intersection there. And then somehow, before I get to I1 where he screws up intersection, we should also know alternative equivalent axioms to the parallel. So equivalent axioms to the fifth, to his version of the fifth. For example, one is that the Amelia, beautiful, sum of angles in a triangle is equal to 180, what he would say two right angles. Another one that we discussed, which is probably the one that most people think of as the fifth postulate, other than Amelia, Nargis. All right angles are equal is postulate 4. And we should know the significance of that. Why would he include that? Isn't that obvious? 90 degrees equal to 90 degrees. Okay, so that's postulate 4. Let me put that somewhere. P4 is that all right angles are equal. Why is this necessary? Okay, so you should know. You know why it's necessary? Yeah, and the way it's defined is when two lines intersect, and two other lines might also intersect with adjacent angles being equal. Who says that this right angle is equal to that right angle? Okay, so there's a kind of conformity around your geometry. It doesn't get weird. If you think about a cone, like an ice cream cone, around most points, there's 180 degrees, but there's this one tip where there's a lot less than you know how on a Lego, you ever play with Legos? Yeah, if they give you a cape is just a flat piece of cloth, but it goes around, you put one bit on the neck and then the other bit on the neck, you put the head on top, and it turns into a cone shape. What you're doing is you're creating less than 360 degrees around a point. That's how you get the cone shape. That's why it has that geometry. Okay, so P4 is saying there are no cones. You have whatever your space is, it's flat. What's another equivalent axiom to the fifth, Alexandra? Yes. Given a line, there is a parallel through the point. Okay. All right. Alexandra.
That there's conformity around geometry for P4.
Why is it necessary? Is that you want to compare some 90-degree angles to other 90-degree angles. And the definition of 90-degree, the definition is local, and you want to be able to use it everywhere. So you need an axiom that allows you to use it everywhere. Amelia and then Layla.
Or like that there aren't any cones.
That there are no cone points, yeah.
So. Is that why he did postulate 4 and then postulate 5? Because like postulate 5 is only true when class.
Yeah, postulate 4, you know, people argue about whether postulate 4 is really necessary. But it is. Yeah. 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 Postulate 4 is necessary. Layla and then Allison.
So postulate 4 only really matters because they didn't have like a way to measure, right?
Well, the definition, so let's write this out. Why is this necessary? The definition of right angle is that when two lines meet, the adjacent angles are equal. If two other lines also meet and have equal adjacent angles, bless you, if two other lines also meet and have adjacent angles equal, how do I compare? How can I compare the equality of angles far away? Equality of angles that aren't adjacent. In other words, let me draw the picture. The picture is, I can compare this angle and this angle because they're right next to each other. And if they're equal, then that's what it means to be right. But here's another pair of angles that also are equal and hence right. And this angle is not adjacent to that angle. So postulate 4 allows us to say they're also equal. That's what the axiom says. The fact that they're both right, even though they're different lines, they're different pairs of lines intersecting, we will hypothesize that we'll always get the same thing. Anna and then Allison.
This is an extremely minor thing, but up there when you're saying like this angle, like theta beta is less than 2 right angles, why would you not just say 180 degrees?
Because they don't speak in degrees. Yeah, he speaks about right angles. He has access to right angles by this definition of right angles. This is one definition that does belong. Definition of right angle.
So would that get marked off if like I were to do that?
No, if you said less than 180, I know what you mean. Yeah. Allison, did I ever answer your question?
But I think it's just to be like extra clear, if you're asking like why is it necessary to have postulate 4, just say so that there's like a consistent definition what the right angle is.
Yes, exactly. That's a great way of putting it. Yeah, you want consistency in the definition. The definition is local. We want it to be able to apply not just locally. Okay. Equivalent definitions to the fifth. Then we got into book 1. So what was the first thing that he does? Book 1, prop 1. He constructs the equilateral triangle, also known as the regular trigon. What's interesting about that, Amelia? Yes, that's what's interesting about it.
Fails with assume.
Yes, it fails to be completely rigorous. You see how careful he's being everywhere else. Fails to be completely rigorous. He's missing axioms that guarantee intersection between objects in general. Intersections between objects. When do circles intersect? When do lines intersect? Not all lines and all circles intersect. Alexander.
22, the triangle equality for purposes.
Sure. Proposition I-20 and I-22.
That's what he was missing in.
Oh, so yeah, if it's 23 or something, I'm not going to ask you about these numbers. I don't know them myself, but what he knows is that he can't, if you're given 3 segments and you're told to make a triangle, if I give you, a triangle of length, if I tell you this is length, I don't know, this is length 6, this is length 12, this is length 30, make a triangle out of those. Okay, so he says you can always do it as long as you can actually do it. Can you make a triangle with length 6, 30, and 12? That would be a good question. Can you, for the quiz, can you make a triangle with length 6, 12, and 30? If yes, do it. If not, why not? There's only one restriction, Jillian. Yeah, let's say I made that triangle. Here's 6, here's 12, here's 30. So you could go from point A to point B and it would take you 30 steps, or you could go to point C first and it would take you a total of 18 steps. That's not possible. The straight line has to be the shortest. Okay, so this triangle cannot exist because 6 plus 12 needs to be bigger than 30, and it's not. It's shorter to go from A to C and then to B than it is to go straight to B. So what's going on there, if you try to follow his construction, is you take one of the side lengths, you put the other two lengths on either side, and then you just draw circles and let the two circles intersect. Oops, these two circles don't intersect. So that's what I mean by he implicitly has the right condition sitting in this other proposition. He just didn't apply it in proposition 1. He knows that circles don't always intersect. If we had something that did satisfy the triangle inequality, you would get a circle here, you would get a circle there, and then here, this point of intersection allows you to draw the triangle with exactly the side lengths that you want. On all pairs.
On all pairs.
Allison. Exactly. Exactly. It's what I'm trying to do. It doesn't look good, but yes, 12 is supposed to be the radius of this one, 6 is supposed to be the radius of that one. If they were to intersect, then there's my triangle, because this is the original length. This is the length that one length that you wanted, this is the other length that you wanted, done. Why do they intersect? He knows that they don't always intersect. He's worried about it in this proposition. He's not worried about it in proposition 1. He should be. Okay. Does that make sense? What else? I'm not going to go into detail of, I want you to know the general structure. So like how it starts, how does it end? How does book 1 end? The Pythagorean theorem. Yes, the converse. Okay, let's go backwards. So I-48 is the converse to Pythagorean theorem, which means I-47 is the Pythagorean theorem. Pythagorean theorem. I do want you to know the windmill proof. That's like one of the big theorems in the book. The windmill proof is the big theorem. The big boss, you would say. What does he do just before then? I-46. Construct the square. Construct the square. Does he take 3 right turns? No, he knows better. So you should know why not 3 right turns. Why use parallel lines? Do you know why? Because on a sphere or in hyperbolic space, 3 right turns. So you mark out 3 paces. You make a right turn. You mark out 3 paces. You make a right turn. You mark out 3 paces. You make a right turn. You won't get back to where you started. Okay, so no, but maybe he tried to do it using 3 right turns, and he couldn't figure out a good way to prove it because he can't prove it because it's not true. So he figured out this other proof using parallel lines. He needed all the information about parallel lines to get up to I-46. The second he had enough about parallels to be able to prove I-46, he could do the Pythagorean theorem, and then he stopped. So why use parallel lines? It's not true in other geometries. Not that he knew about them, but he couldn't have possibly proved it. So there can't be a proof that avoids parallel lines. Squares don't exist in other geometries. You can take 3 right turns in other geometries. You just won't get back to where you started. Okay? Yeah. Yeah. Alexandra.
Don't live like on a plane that uses linear geometry.
we live on the earth, which is why he couldn't prove it, but like if he didn't want to.
So, it's more subtle than that. It has not, it's not, I would say, the fact that we live on a sphere or that space-time has hyperbolic components. If there was a logical argument that could prove the construction of a square using three right turns that doesn't use parallel lines, well, then those axioms are just as satisfied on the surface of a sphere and in the Beltrami plane or the Poincare plane, the hyperbolic plane. So that argument can't possibly work since there are no squares in those geometries. Does that make sense? Alexandra?
Fine, it's not true, it's just saying that making three right turns.
Yeah. That's right. Making three right turns won't, or I guess, what is it? Yeah, that's one right turn. That's a second right turn. Make a third right turn. Get back to where you started. You won't come back to where you started. Right angled turn.
Okay.
Yes. Yes. Okay. Same thing. Yeah. Right angled. Three right angled turns. Josie. Except parallel lines don't exist in the same way. There's not a unique parallel line. In hyperbolic geometry, there are no parallel lines in spherical geometry. Yeah, that's a great question. So I really want to answer your question, but I know it's going to take us a little too long. If you actually sit in other geometries and try to work through the arguments, for example, one of the things that he proves is if you have really what he's using is something about areas. And if you have a parallel, remember we had this thing about if you have a parallelogram on a base and a triangle that whose tip is on the same parallel, that those have the same area. That is just not true in hyperbolic geometry, in other geometries. In spherical geometry, it's not true because there are no parallel lines. In hyperbolic geometry, there are too many parallel lines. You have way too many degrees of freedom. And triangles can have lots of other different areas not related to the area of a parallelogram. Does that make sense? In order to justify that statement, I would need 30 minutes, and I don't want to take those 30 minutes, if that's okay. All right. I just wanted to show you that there's something subtle here, that he's not just doing it some stupid way. When we go to GeoGebra, we just make three right-angled turns and we're done. Why doesn't he prove it that way? Because he can't. Not because he's not good enough, because it's not possible. Okay. That was book 1. We did spend some time on book 2. Did we? A little bit. Okay, so book 2, let's just say book 2 ends with, anybody remember who the big boss is? That is a good guess. That's book 4. It ends with the 15 gone. We're coming to that. Quadrature, yeah, ends with the quadrature of the rectangle. Book 3. Do we talk about book 3 very much? Not really. We talked about, yeah, circles and tangents and circles, tangents. Like the first thing is how to find the center, how to find the center of a circle. That's a good, I think that's fair game. You should know how to find the center of a house. No, but we did that already. We did that already. No, I'm just reviewing sort of what we've gone over. You know, yeah, that book 2 ends with the quadrature of a rectangle. I think that fact is basically all that I would want you to be able to tell me. And then book 4, as Layla told us, ends with, so he's worried about regular n-gons. Regular n-gons ends with, so constructs the 5-gon, constructs the pentagon, and from that and the triangle plus the 3-gon constructs the 15-gon. Hello, thank you. Oh, I see. Constructs the 15 gun.
Would you like us to be able to do the conversion of the 15?
I would like you to be able to tell me how, given a pentagon and a triangle, you could come up with a 15 gun. Yeah. Well, we didn't go over the construction of the pentagon. So I can't ask you to construct a 15 gun because I can't ask you to construct a pentagon. But if someone gives you a pentagon already, so given, sorry, yeah, given the 5 gon and 3 gon, how to construct the 15 gon, and it's very simple. Let me just remind you, if all of these regular n-gons are being constructed in a circle, so if I draw a pentagon and I also draw an equilateral triangle, and I can find the center of the circle, even though maybe I forgot to draw it initially, what is this angle from here to here? That's the key. Or maybe this one's even easier for you guys to see. Yeah, well, how big is this angle? Yeah, 120. This angle is 2 pi over 3. How big is this angle? How do I draw it like that? How big is that angle? 2 pi over 5. And therefore, how big is this angle? Yeah, it's almost 2 pi over 15. It's 2 pi times 2 over 15, because a third minus a fifth is 2/15. And so if you bisect this angle, then this much is 2 pi over 15. Lori.
So is it matter where you put the points in the triangle?
Let me try to do a better diagram. Geometry. Okay, get rid of the axes, get rid of the grid. Okay, construct a regular polygon. So let me get a little, oops. Let me get a little line segment. Here's a little line segment, and give me a regular. And by the way, do you see what shape it has in the tool? The n-gon tool. Can you see that? It's a pentagon. Can I zoom in? No. Okay, it's only going to zoom in. No. Go away. Okay. All right, here's my pentagon. Let me draw a circle that has the pentagon in it. How am I going to do that? I guess I'll take a pair of points and draw a perpendicular bisector. Where's my perpendicular bisector between 2 points? Here we are. Here are 2 points. Here's the perpendicular bisector. And then here's another perpendicular bisector. And those 2 perpendicular bisectors meet at a point. And now let's draw a circle with center at this point, radius there, bless you. There's my pentagon. Okay. How am I going to inscribe a triangle in this pentagon given 1 point? Well, I could take an equilateral triangle with base, let's see. I could make an equilateral triangle with base DC and then grow it. How do you put them both in the same place? Never thought about this. All right, here's what we'll do. We'll just put an arbitrary, we can put, here's what we can do. We can do a parallel line to this line through this point. Then we can draw an equilateral triangle at that point on some segment. I'm sorry to be doing this in front of you. Okay, so there's a little segment. And now we can draw an equilateral triangle on that segment. Is this going to work? Please? No. Oh, regular polygon. Sorry. I want a regular polygon. This was a mistake, wasn't it? This is going to take way too much time. Okay, so there's a triangle. I actually want that triangle centered at that point, not because I want to draw. This is not going to work. I think let me try to just draw a better version of this picture than instead of trying to do it in GeoGebra. Here's a slightly better circle. I'm going to make the pentagon in red. Okay, so suppose I can construct a pentagon in a circle. The problem is that I constructed the pentagon first and then the circle. So I would have to, yeah, the right way to do this is to construct the equilateral triangle, then to construct the circle, then to construct the pentagon inside of it, but we don't want to go through that process. So that's the pentagon. Then the green will be an equilateral triangle with this same point. Okay, and then there's a center here. That's the center. So if I look at this angle is what we said before, 2 pi over 5. Does it make sense why that's 2 pi over 5? It's the same all the way around. I'm cutting the pentagon into 5 triangles. And so this angle, there's 5 copies of it, and they're all the same. And so we've cut up 2 pi into 5 copies. Okay. Then there's another angle, which is this angle to here and to there. That big angle, that green angle, is 2 pi over 3, 120 degrees. For the same reason. And so the new angle, I guess I'll make it black. This angle here is 120 degrees, take away 2 pi over 5. That make sense? Everybody with me? So this is 2 pi over 3 minus 2 pi over 5. If you work out what that is, it's 2 pi times a third minus a fifth, which is 2/15. And so if you were to bisect that angle, is yellow a good color? Can you see yellow? You can't really see yellow, can you? Oh, kind of can. Okay, then this angle here would be, I can't see that, 2 pi over 15. What? The yellow line is a bisector of this line and this line. It's the angle bisector between those two. So the black angle is twice what I want. So if I bisect that angle, I get the yellow angle, which is not 2 pi times 2 over 15, but 2 pi times 1 over 15. And so once I can make that angle, I can copy that angle and go all the way around, and that'll make the 15 go. Lori, is that better? No. Okay, where did I lose you? Let's start with the red. Are you happy with the pentagon's internal angle being 2 pi over 5? This red angle is 2 pi over 5. Are you happy with the green angle being 2 pi over 3? The green angle is going from the center of the circle to one vertex of the triangle and to another vertex of the triangle. So if you take a triangle and you cut it into thirds from the center, you get these 3 isosceles triangles, the third one being over here. Let me draw it in the same color. So I have these 3 triangles with internal angle. Well, it's the 3 of them are all the same. And there's 3 of them, and they cut 360 degrees in 3, so they're 120 each. So the green triangle is 2 pi over 3. The green angle is 2 pi over 3. The black angle is the difference of the green take away the red. Black is green minus red. And if you work out what a third minus a fifth is, it's 2/15.
That wasn't, I mean, I guess it's in the triangle, but you only did it using pentagon? I guess it's hard for me to see now with all of the.
Can you tell me the red angle with the pentagon?
Yeah.
Yeah, so that's just a fifth of the pentagon. And the center of the pentagon goes all the way around 2 pi.
Until we got to, 2 pi over 3 minus 2 pi over 5.
Yes.
Pi times 2/15. And I understand why if you bisect, then that the yellow angle, then you would get 2 pi over 15, but why do we want to do that?
Because if you can make an angle that's 2 pi over 15, then you can continue making an angle that's 2 pi over 15, and you go all the way around, and you have 15 equally spaced points on the circle. That makes a regular pentagon. That's the 15 guy. We're trying to.
It wouldn't make a shape if you bisect it, is that wrong?
Right. If you had a 2 pi over 2/15,
Yeah.
as you start going around, you will only get 7 points, and you'll jump over the next point. Yeah. We're just trying to construct 2 pi over 15. If you can construct an angle with angle 2 pi over 15, you can follow it around. We almost did it, except we got twice as much as we wanted. So bisect it, we get back to the amount we want.
Kind of like pick the center, is there like a way we're gonna have to show that we knew what the center was? Like when we drew the red and the
Yes. So knowing what the center of a circle is book 3, proposition 1. And we just did it in GeoGebra when I was trying to figure out how to draw this picture quickly. Yeah. If you have a circle and you don't know where the center is, yeah, take 2 points and take the midline and do it somewhere else. Here's 2 more points, the midline. The midline is a set of all points equidistant to those 2 points, the perpendicular bisector. And so the center will lie on both of the perpendicular bisector. Amelia. Yes.
6 equilateral triangles with the radius as the sideline.
Yes, that's a good way of doing it. I like it. I like it. I like it. Beautiful. Beautiful. That's exactly the right way to do it. So if I just take a radius and give me an equilateral triangle, and now give me another equilateral triangle. Okay, so that angle right there is 120 degrees. I don't know. Can you really see this? And now I'm going to draw an equilateral triangle from D to K. There it is. There's the equilateral triangle on top of a pentagon in the same circle. Awesome. Thank you. That's the right way to do it.
Print it out and draw arrows to angles or explain it in words or.
Yeah, explain it in words. Why does a 5-gon and a 3-gon together give you a 15-gon?
Just saying.
This right here is the key equation. Because a 5-gon, the angle on a circle in a 5-gon is 2 pi over 5, for a 3-gon is 2 pi over 3, and their difference is almost the angle you want.
I get the equation itself. I don't get like, can you just do it like with every step to show how it equals 2 pi times 2 over 15?
Sure. You mean here? So the 2 pi's pull out, and then we have a third minus a fifth. So far, so good. And then a third is 5/15, and a fifth is 3/15. That's all. Sure. Okay. I didn't have in mind for that one to take us on this big whirlwind, but like, remember why are we studying this book with so much detail, right? This is the only document that we will go through in anything remotely resembling depth. Why? Amelia.
Really what mathematics was at that time, like all the, not all.
Yes.
that would be
That's one half of the answer, is that Euclid beautifully summarizes nearly all of the mathematics known, certainly known in space-time at that time and in that place. He does a beautiful summary. And Nargis? Yes, he has a beautiful exposition of things and a very logical layout of the books, and rigorous proofs, and yes, the impact this book had on so many generations and millennia worth of mathematical research. We already talked about how book one gave rise to non-Euclidean geometry. Oh, we didn't. I skipped that entire discussion after book one. Okay, so in here, star, the whole point of going in so much detail into book one was to then talk about non-Euclidean geometry and the various people involved in discovering it, including Lobachevsky, Bolyai, Janusz Bolyai, Carl Friedrich Gauss. This is all like 1830s. Then we talked about Riemann. That, Lori.
But when you have the 2 pi 215, you need to bisect that angle to create the angle you need for the 15 gone. You can't do that.
Well, the 2 pi over 2/15 is not the angle we're looking for. We're looking for the center of that 15 gon, right? Just to drive home the point, if I can make an angle here that's 2 pi over n, then if I extend that to here, I can copy that angle again, and I make another 2 pi over n, and I make another 2 pi over n, and I make another 2 pi over n, and I just keep this going. And I come right back. This is an exact division of the 360 degrees around this central vertex into exactly n copies.
Yes, but I'm sorry, I don't think when you have 2 pi to 15,
Yes,
is that the necessary angle for 15 gone, or do you need to bisect it so it's
I need to bisect it because I need there to be in order to get an n-gon, I need the angle to be 2 pi over n.
Yeah.
In other words, 2 pi times this unit fraction, 1 over n. And we don't have a unit fraction, we have 2 over 15. That's what's missing. I need a 1 in the numerator. Does that make sense? So once you have all those points, then you connect the points and you get your regular whatever it is that I've drawn. Does that make sense? Nargis, good? Or a question? No. Okay. Back to non-Euclidean geometry, we talked about Lobachevsky, Bolyai, Gauss, Riemann. That Riemann, Gauss had ruled out the angles being the sum of the angles in a triangle being more than 180 by saying it has to be infinitely long. No lines don't have to be infinitely long, just unbounded. There's no bounds in the geometry. You can always extend them, right? So we want P2 to be satisfied. But P2 doesn't say that they have to be infinitely long. And finally, Beltrami, this is in 1868, I want to say. Again, I'm not quizzing you on the numbers. Just know that Beltrami comes after Gauss because he puts the whole problem to bed, the last nail in the coffin. What does Beltrami do? He introduces the concept of models. Models, yeah. That geometry should be understood in terms of models. He introduces the disk model, in particular, the disk model. Now, we didn't actually go over Beltrami's disk model, which is actually known now as Klein's model. But we did talk about M.C. Escher, which is 1950s, rediscovering independently a model due to Poincaré's model for the hyperbolic disk. Allison.
Just for this, but it's just understanding the timeline, and like what was proved, not essentially going through like.
Yeah, it's 15 minutes, right? There's not proofs, it's like what is what does line segment mean in this Poincare disk? I give you 2 points. So this is a good, oh yeah, it's supposed to give you like sample questions. So here's a sample question. You have 2 points in the Poincare disk. Let me draw them a little bit more like that. Hand draw. So here's a question. Hand draw line segment through them, or the full line. That's a better thing to do. I don't know what just happened. Line through them. Layla.
So, I have 2 clarifications, but MC Escher is the artist.
Yes.
Also, Poincare's model is that the one that goes like all the way around, like the globe shape?
Poincare's model is the disk that we discussed. So the plane is the unit disk, the interior of the unit circle. Points are points, and what are lines? So what is the line through these 2 points? Jemima. The arc.
Get the word, is it
Orthogonal, yeah, at a right angle. Yeah, you have to find a way to have a circular arc that's orthogonal. So answer circular arc that is orthogonal at right angle to the boundary, to the bounding circle. Okay, does that make sense? Get rid of this. Good. Okay, so that was our discussion about oh, and so why the existence of models proves. So here's another question. Why, sample question, why does the existence of other models prove that the parallel postulate cannot be proved from the others? Amelia.
Because, like, if we were to use an equivalent to the parallel postulate, so parallel postulate is postulate 5, right?
Yep.
So then, like, in this model of, how do you say it?
Poincare.
Poincare model, like, if you were to draw a triangle, don't the angles equal more than 180?
On a sphere, they equal more. In the hyperbolic plane, they actually equal less. So if you just, you could say Riemann. You could say that Riemann's model allows for spherical geometry, or really, it really allows for projective geometry. These are slightly subtle things that I'm trying to avoid talking too much about. But so here's a sample triangle in the Poincare, an attempt at a sample triangle, and these 3 angles add up to a lot less than 180.
Yeah.
Did I answer your question? Yeah, okay. Nargis, Alexandra, Layla.
Models, y point, and they're like, they're like undefined terms, but they're still using all the models
Yes.
in hyperbolic geometry. With postulate 1 through 4, then you can't do it in any of the other models either.
Exactly right. So another way of saying that is that every fact in the hyperbolic model is also a fact in the Euclidean model, just with the words, just with the undefined terms, point, line, plane, circle, shuffled around. They have different meanings, shuffled around. So you're not going to find a contradiction in the hyperbolic model that you didn't already have in the Euclidean model. So there are no new contradictions in the hyperbolic model that didn't already exist in the Euclidean one. So the way of saying that is that these two models are equally consistent. These two models are equiconsistent. They're just as each is just as valid. Okay. Alexandra, Layla, and Lori.
I guess I'm missing the link between how this proves that the fifth postulate can't be proved from the other four.
Yeah. So how would you try to prove that the fifth postulate is necessary? You would say, suppose it fails. Suppose the fifth postulate fails, then we'll come up with a contradiction. Well, that's a synthetic question. That's a purely, that's a question that's not thinking about a model. It's thinking about the axiomatic structure of Euclidean geometry. But now we can say, okay, here's a model that satisfies all the axioms. And in this model, suppose we can find a contradiction in hyperbolic space. When we assume that the parallel postulate fails, suppose we can find a contradiction. If we did, that would be a statement about circles and lines, and we can make that exact same statement in the language of Euclidean geometry, just when we change what the meaning of the words, the undefined terms is, the mapping from undefined terms to actual literal like line segments or circles of arcs or whatever. So if there's a contradiction in hyperbolic geometry, then there's also a contradiction in Euclidean geometry itself. That doesn't mean there isn't. We haven't proved yet that there isn't a contradiction in Euclidean geometry. There very well may be, in the same way that the Pythagoreans had an assumption, this axiom of commensurability, and they were doing all of their geometry with this axiom, and it turned out that their geometry had a contradiction in it. And everything fell apart. So we do not, at this time, have an understanding of whether Euclidean geometry is or isn't consistent, whether there are whether from the axioms that Euclid sets out, whether there are false statements that can be proved, like root 2 is rational and irrational. Oops. So, but that's not the question. The question is there new contradictions that can arise from assuming the failure of the parallel postulate? And the answer is no. Anything that's a contradiction in hyperbolic geometry is also a contradiction in Euclidean geometry, just with some other statement.
The issue to bed, it just says that you can't find any new.
Right. It puts the issue to bed of whether the fifth postulate can be proved within the Euclidean system from the other four. It does not put to bed whether Euclidean geometry itself has a contradiction. So this is the difference between the consistency of Euclidean geometry, whether there are no false statements there are no contradictions that can be proved, versus the equiconsistency of Euclidean geometry to hyperbolic geometry. Each geometry is just as consistent, just as right or wrong as the other, because there's a mapping from statements in one to statements in the other. And if such a mapping exists, then it can't possibly be the case that from just the four axioms that are common to both hyperbolic and Euclidean geometries, you can derive the parallel postulate. Because if you could, then you would also derive it in hyperbolic space where it's just not true. So that's a really good subtle point. And I hope it's clear. Layla and Laura.
So basically, in the other models, parallels don't exist, right?
In hyperbolic space, parallels do exist. There's just infinitely many of them. And yeah, let's write that down, since that's an important fact to keep. Recall, in the hyperbolic plane, parallels do exist. There are too many of them exist. Too many. In the spherical model, there are no parallel lines.
It's like, I think I'm confused here because like, if they exist in one and don't exist in another, is that not a contradiction?
No, because they're different geometries. They're different worlds. They are not both being derived from the same set of axioms. One set of axioms says, given a line and a point, there's a unique parallel. That's Euclidean space. Another says, given a line and a point, there are no parallel. Any other line you draw is going to intersect that line. That's spherical geometry. And another says, given a line and a point, there are infinitely many parallel lines. So if I look at this line and this point, here's one parallel line. These don't intersect. Here's another parallel line. These still don't intersect. Here's another parallel line. They still don't intersect. There are infinitely many lines that I can draw that pass through this point that do not intersect this other line. Okay, that's another good sample question. Given in the hyperbolic disk, given a line and a point, draw a parallel line to that point. Here's another good sample question. Given in the hyperbolic disk, in the Poincare model of the hyperbolic plane, given a line and point off of the line, draw two different parallel lines through the point. That's a good one. Lori.
Say model this effectively, but every like all of the eyes, all of the propositions. It's not about like an axiom as opposed to the axioms.
No, what I mean is when you have the proposition that 2 points that between given 2 points there exists a line. Let's do an example of that. Where is this? This example. Okay, so here's an example. In hyperbolic geometry, there's a P1. P1 says given any 2 points, there exists a line segment through them. Right? That's postulate 1. Given 2 points, there's a line. What does that statement say in Euclidean geometry, in the corresponding statement in Euclidean geometry? The statement is, answer, given a circle and 2 points inside the circle, there exists a further circle passing through those 2 points and meeting the given circle orthogonally. So when you change your meaning of the words, forget that this was what hyperbolic geometry is supposed to be. Just think about what the statement is. It's that given a circle, just a circle, and 2 points inside that circle, there exists another circle that passes through those 2 points and meets the original given circle at right angles. That is a statement that you can make perfectly well in Euclidean geometry. Its interpretation in hyperbolic geometry is P1. Given 2 points, there's a line. So that's what I mean by there's a correspondence between statements in hyperbolic space and statements in Euclidean space, but you have to change the meanings of all the words, but it has the same picture, Amelia.
Just put it in Euclidean, just would be drawing a connecting line between two.
Correct.
This is what model like the hyperbolic geometry in.
That's right. That's right. There's a way of modeling hyperbolic geometry in Euclidean geometry when you change the meaning of the words. That's exactly what I mean by that. Okay, so that's what I mean by any statement that you can make in hyperbolic geometry also has a corresponding statement in Euclidean geometry, which is just as valid. It's the same picture. We're just reinterpreting the same picture in 2 different ways. In one way, it's about circles and points. In another way, it's about straight lines in a plane. Nargis.
Is a further circle. Why isn't it just the 2 points inside the circle?
Well, there's so there's a given circle. Let's make the given circle red, please. We're given a circle, so that's the original circle that we're given. And then I'm trying to construct a second circle. So the further circle is the blue circle. The further circle is the blue circle. I don't want to say there exists a circle. Well, I'm just saying there exists a circle. So you don't like the word further. Strike the word further from the record. There exists a circle that passes through those points and meets the original circle orthogonal. Let's take me back. Something's not clear.
Like, what, like,
Oh,
line segment and Euclidean.
yes,
Why is it a circle?
because that's the model. So what Poincaré realized is that there is, and what Beltrami realized before him, but with a model that's a little harder to explain, is that there is a way to express any statement in in hyperbolic geometry as a statement in Euclidean geometry. And this is it. And this satisfies P1, P2, P3, P4. Given any segment, you can extend that segment a little further. That's P2. I have to tell you what distance is in this model to explain what a circle is. All the points equidistant from a given center. Okay, I think we're getting a little hung up on this. It's not meant to be. This is a little 15-minute quiz, but these are important concepts. The fact that we're reviewing them is good because we're locking in their meaning. Joseph.
Like translating from one language to another.
Yes.
Whereas before we were talking about speaking like the same rules of a language, but in different terms, right? Like there exists like the equivalent of a point in Euclidean geometry in other geometries.
Yes. Yes.
But we can translate those other geometries into Euclidean geometry if we want.
Yes.
It's just like those are, I feel like that was really confusing, like the distinction of what we're doing. And so I'm still confused though on the like conclusion of like the P4, like all the first four postulates and how they can't be used. Is that related to this distinction between translating versus like?
The fact that there is this translation between any statement in hyperbolic geometry, which is a statement about what we used to call lines and points in a plane, but in Euclidean, when we make the translation, they're called circular arcs. And instead of a plane, we'll say disk. The fact that this translation exists means that I can't prove a new contradiction in hyperbolic geometry. It isn't already a contradiction, just with different words shuffled around in the translation.
So that is a contradiction in geometry. To P5 if there is one in the other geometries? Or is it not, the relationship doesn't go that direction?
Okay, so this is getting a little bit farther along in the world of logic and almost philosophy. So there's Euclid's geometry. We have not proved that Euclidean geometry is consistent. Pythagorean geometry, we did prove is not consistent. You start with these axioms. They said these are the things we hold to be self-evident, including the axiom of commensurability, and we proved a false statement. So we proved that those axioms don't work. You can prove false statements within those axioms. We have not proved that, given the 5 postulates that we start with Euclid, that we do not arrive at a contradiction from those axioms. What we've proved is that if you are to arrive at a contradiction in hyperbolic geometry, the way that people were trying to prove the 5th postulate from the other 4 was if it doesn't hold, then you'll find a contradiction. And the answer is, if there's a contradiction here, that has a translation to something that's also a contradiction here. So they're just as valid theories. So just the fact that you added or took away postulate 5 doesn't change the validity of the theory. And that means you can't prove postulate 5 from the other 4. Because if you're going to prove it, you're going to find a contradiction by its negation. But here's something that has the same potential pitfalls or the same truth as the thing without postulate 5 being true. This is a really subtle thing and something that I think is, we could spend a long time talking about Gödel and completeness and incompleteness of theories.
Dumb down. So like that's the Euclidean geometry trying to show what we know in.
It's an example of a translation. exactly as I think Josie put it really well, that there's this translation between the language of hyperbolic geometry and the language of Euclidean geometry. But the meaning, the underlying meaning, the picture that we draw to understand it is the same picture.
So is hyperbolic geometry like in Euclidean geometry?
It's the translation from a statement in hyperbolic geometry to a statement in Euclidean geometry that has the same underlying meaning.
Geometry, the lines aren't particularly straight.
Right. The reason we use a circle is because Poincaré is really clever and came up with circles as a way of making that translation possible. So this is really subtle stuff. I don't mind spending some time on this because this is really subtle, and I want to make sure we get it right. Allison, then Lila. P1 through P4 hold in any geometry, and then P5 holds in Euclidean geometry, fails in hyperbolic geometry, fails in spherical geometry. But
So is this drawing Euclidean or hyperbolic?
both, depending on who's looking at it. It's like there's a statement, you know, we see a bunny rabbit, and I'll say bunny rabbit in French, and you'll say bunny rabbit in Spanish, but we're both pointing to the same bunny rabbit. Right? We have different words, we have different ways of expressing what it is, but the object is still the same object. So in this way, there's a different way of expressing this picture. One way is through the language of hyperbolic geometry, where we would call this thing the straight line segment between these 2 points, with the red being the boundary of the plane, and the other one is just, no, we have 2 circles and they meet at right angles. It's still a bunny rabbit, but we're going to call it different things in different languages. Okay, almost there. So to cycle all the way back to, I think, Amelia's answer to my question about why do we care so much about Euclid, is not just that he put together in this great way all of the mathematics that was known at that time, but the impact it had on millennia of mathematicians that came after it. And when we talked about the 15-gon, so now I need a double star to recurse out of that recursion and to double star what came after the 15-gon, the 17-gon. Okay, so then millennia later, this is 1796, 19-year-old Gauss discovers that not only can the 3, 5, 15 gons be constructed and all of their doubles, right? You can bisect an angle, so you can make a 6-gon, a 12-gon, a 24-gon. You can bisect the 15-gon, make a 30-gon, 60-gon, 90-gon. But also the 17-gon can be constructed. By the way, he wanted the 17-gon on his tombstone. He was so proud of this. You know, despite all of the other things. What's that? The story goes that they asked the guy who makes the stones, you know, can you make a 15-gon? And he's like, yeah, it'll just look like a circle. You won't be able to tell. There's too many points. I mean, the 17-gon. He wanted the 17-gon on his tombstone, and it just looks too much like a circle. There's too many points. Okay, Gauss discovered this. Why? Why is the reason? By the way, 17-gon. Let's see, the heptadecagon. Here's the reason. This is the reason. What he really works out is that cosine of 2 pi over 17, that's the angle that we would care about. Why cosine? Because cosine is what happens when you drop this over here. If you can make that length, then you can make this angle. Right? We talked about trisecting angles and the constructibility. Look at that number. What do you notice about that number? It's 2 pi over 17. How about the thing on the right? This is what he doesn't actually construct. It has radicals.
Isn't that like a big thing about you can't construct something if it has like a cube root?
Yes, you cannot construct something that has a cube root, but you can construct it if it only has square roots.
Oh, so it is constructible?
Square root, 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 square root. Nothing but square roots. That's what he figures out. This is really what Gauss.
What a genius.
And he was 19, yeah. The reason cosine of 2 pi over 17 can be written in terms of square roots only. That is, it is a constructible number. It is a constructible number. And the bigger reason, I mean, the why is 17 a constructible number? It's because 17 is a Fermat prime. 17 is a what is now known as a Fermat prime, and Fermat primes are numbers of the form, that is a number of the form yes, plus 1, 2 to the 2 to the m plus 1. Okay, Fermat, the reason it's called a Fermat prime is that Fermat was looking at numbers of the form 2 to the n plus 1, and he said the only chance that number has of being prime is if the n itself is a power of 2, so 2 to the 2 to the m plus 1. And
Wait, is it 2 to the 2 to the n plus 1?
No. Maybe I'll do 1 plus, since I hate PEMDAS. Okay, it's 1 plus 2 to the 2 to the m. Okay, so we saw that 3 is, and so are 3 and 5. 3 and 5 are also Fermat primes, but they're kind of, you don't think of it because they're too small to see what's actually going on. Gauss finally figured out what's going on, and he proved this theorem that the only constructible n-gons are these. These has a subtle meaning to it, because you can take a 17 times 5 gon in the same way that we saw before. That we can take a 15, we can make a 15 gon out of 3 and a 5. You can make a 3 times 5 times 17 gon by mixing all of them together. What you can't do is make a 5 squared gon, a 9 gon. You can't mix triangles and triangles because it won't work. You can't trisect the angle of a triangle. You can't 5-sect the angle of a pentagon. But when you have a triangle and a pentagon against each other, that's when you can make this 2/15 angle. Okay. That's the review, and that's the whole class. Okay. Can we?
Yeah, for real, I'm a little intimidated.
There's a lot to study. I'm actually impressed. I thought we were not covering all that much, but in 2 weeks, it's been 2 weeks since the midterm. We've covered quite a good amount of material. Good. You're getting your money's worth, right? You came here to learn something. The exam itself will cover a tiny fraction of this because it's 15 minutes, right? You've seen it, what a quiz is, like 3 problems, and potentially a bonus. Okay, Amelia's putting in the vote for the bonus. Amelia. What can I do in 10 minutes? I think we can cover at least a little bit of new stuff in 10 minutes. What do you think? All right, let's do a little bit of new stuff in 10 minutes. Let me just keep going. So that was books 1 through 4. Let me hop over here. Okay, so book 5, on to book 5. New stuff is book 5. What's in book 5? Let's open up book 5. Here's book 5. This is all about, it's a good way of describing this. It's all about proportionality. So book 5 is all about proportion. Actually, there is a story here. Let me show you who the big boss is. The big boss is kind of a nice little theorem. Let me come back to the big boss. Here's what happens. Book 5, you remember there's, let me draw you a little picture. You remember there's the Pythagoreans. So this is the year 550 BC. We have the Pythagoreans. They have this axiom of commensurability, right? As we just discussed, axiom of commensurability, which turns out to be wrong. They discover that due to Hippasus, and he turns out to be wrong. Yeah, he turns out to not swim. Then we get to Hippocrates, Hippocratic loon. I'm just trying to and the loon. 350, this is not to scale. 350 is just Alexander the Great. And in particular, the city of Alexandria is created around this time. 300 is when we get to Euclid. There's a big name that I've mentioned in passing, but we did not spend any time on, which is Eudoxus. Eudoxus is around 350 of Cnidus. Not that it matters. This is like modern Turkey. Eudoxus is important for many reasons. One of the reasons, remember, Hippocrates writes a version of the elements. This is the first version of the elements. Eudoxus writes another version. And finally, Euclid is the last version. The important thing that Eudoxus does, and Hippocrates' version is not that great because Eudoxus fixes everything. He goes back to the Pythagoreans, and the fact that they prove all of their theorems using this axiom of commensurability that they know is wrong. They still think the statements are right, but they don't know how to prove them properly. So the state of affairs before Eudoxus, people believe that statements that were proved using the axiom of commensurability are correct. They believe that the statements are correct, but they know that the proofs are invalid because they use a postulate, an axiom that they know leads to contradictions. Okay, so for example, the way they would deal with similar triangles, I think I mentioned this just to remind you, if you have similar triangles, so here's one set of triangles and then another set of triangles, okay, and this is like, this angle is the same as that angle is the same as that angle, and this angle is the same as this angle. And they would prove things like, well, if this is A and B, and this is, I don't know, alpha and beta, then the ratio of alpha to A to alpha is equal to the ratio of B to beta, right? This is the kind of thing that you would want to do with similar triangles. Similarity means that the sides are in proportion. And the way the Pythagoreans would prove it is that they would find a common measure. So Pythagorean approach, find a measure common to both A and alpha. Okay, in other words, find a little unit. Here's a little unit, U, and U will measure A equally, and it'll also measure alpha equally. And then you know what this ratio is. It's like 7/12 or something, right? Every ratio is a rational length. And then they would have to argue that when you find something that measures B and beta, it will also be 7/12. And then argue that beta B over beta has the same whole number ratio. Well, guess what? Not all ratios are rational. So the proof is wrong, right? The proof, the part where we say, oh, that's probably like 7/12, that's wrong. But the statement that they're in proportion is still right. And they couldn't figure out how to fix this. This is where Eudoxus comes in. Eudoxus is the one who fixes up the whole theory. And Eudoxus develops properly the theory of proportion and fixes the Pythagorean geometry to not use the fallacious theory of axiom of commensurability. Okay. And book 5, please. And book 5. Book 5 is that theory. Is Eudoxus's work. So if we look at book 5, let's go to proposition 1 just to show you what it looks like. if any number of magnitudes are the same multiple of the same number of other magnitudes, then the sum is that multiple of the sum. The hell is he saying? There's probably this is expanding out a sum. Okay, if any of these are all multiples of the same thing, then their sum is also a multiple of the same kind of thing in the same way. It's the one piece of the distributive property. Yeah, it's the like, you know, distributive. Yeah, it's a distributive property on across sums. It's something. So you have these, you know, parts have the same ratio as their equimultiples. Like, let's not even you know, if you converted this into, if this is saying that if C, the ratio, the proportion of C to F is the same as the proportion of NC to NF, right? Let's just record 15. So this is 5.15 says C over F is equal to N times C over N times F, right? This is like not a very exciting mathematics.
So what is the difference between what he's saying and what the Pythagoreans said?
It's not what they're saying, it's the way that they're proving what they're saying. The Pythagoreans would reason about this this ratio by saying, find something that measures both C and F. So C is some length and F is some other length. And they would say, step one, in order to prove this theorem, so what is N times C? It means take C and multiply it some number of times, and take F and multiply it by some number of times. Make sure the same number of times. Okay, so this is NC and this is NF, and the proportion of this to this will be the same as the proportion of the original ratios. They can say it all in lengths. The step one in the Pythagorean argument is cut C and F into a unit that measures both equally. That's the step that you can't do. But you don't actually need to do it in order to prove the equality. Okay. Let me show you the big boss here, because this is one thing that has some mathematical content. It's not entirely trivial. Proposition 25 is the big boss. 525. That's kind of cool. It says the following. Let me read it in his. If four magnitudes are proportional, then the sum of the greatest and the least is greater than the sum of the remaining two. What he's saying is, if four values are proportional, so if x over y is equal to z over w, that's four values being proportional. Let's read it a little closer. Let the four magnitudes a, b, c, d, e, and f be proportional, so that a, b is to c, d. So I'll write it in his language. Here's a to b. A to b has length x. It's proportional to CD. CD has length y. And let AB be the greatest and F be the least. So then he has another, he just calls it F. He doesn't bother giving another name, but this is Z and this is W. F and G. Okay, so if the proportion of x to y is the same as the proportion of z to w, then here's the theorem. The sum of the largest plus the least, x is the largest, w is the least, exceeds the sum of the other two, z plus y. Let's just read that. I say that the sum of a, b, and f is greater than the sum of c, d, and e. So you might think about how you would prove this kind of thing. This is not entirely trivial. Should I give you a proof in 30 seconds? You want to think about it? Neither? Don't think about it and don't give a proof? It's really easy. Let me show you in 1 second. What this means, if x is the bigger one, then let's say both of these ratios is some a, right? So x is equal to a times y, and a is bigger than 1. Well, z is also equal to a times w, right? That's what it means that they're in the same proportion. So if I subtract like x minus z is equal to a times y minus w, right? That's some distributive property type thing, type argument. And what that means is that x minus z is greater than y minus w. That's it. Because a is greater than 1. You happy with that? Now you're done.
For next one.
And points.
No, A is a quantity. So I'm saying if X is a length and Y is a length, then X over Y is is a number. Is the ratio between them. This isn't so important. We pick up on Thursday and hopefully we'll make some actual progress.